And we're going to hear from Alex Kamenev, and he's going to tell us about rare events in phase transition and reaction diffusion systems.
Thanks. Good afternoon. I wanted to tell you a story about reaction diffusion systems, which started from the discussions with my former graduate student, Vlad Elgart. Some of you here may know his twin older brother, Alex Elgart. And then later continued with my colleagues from Jerusalem, Baruch Meyerson and Michael Asaf. All right, so what is reaction diffusion systems? This is a game which is specified on a lattice. So imagine you have d-dimensional lattice and then some agents which live on this lattice. These agents may be molecules, or it may be viruses, or it may be animals or stock options, whatever you like more. So one very common example in chemical kinetics is that two molecules form stable aggregate, like H2 or whatever, and segregate from the reaction and does not participate in reaction anymore, so we call it zero. Another very famous example is coming from immunology, where you have so-called susceptible, infected, recovered, or some people call it susceptible, infected, dead, or whatever, again, you prefer, where you have susceptible individuals, and then if they meet an infected individual, then there are two infected individuals, and then the fate of infected may be either recovered, or again, susceptible, or whatever.
Not so good.
Happens. All right, now two things to notice about these games is two things. First of all, it is not specified by Hamiltonian as we accustom in physics, but rather by dynamical rules, what happens if so many agents meet or collide, or whatever you call it. That's one thing. Another thing, that there is an intrinsic discreteness in this game. So there is only integer number of agents which can be on a given site. Right? Now, what I'm going to tell you about is that despite being formulated as a game, these models have very nice and clean Hamiltonian language to talk to. And it's, as usual, once we have Hamiltonian language, it's very useful. In particular, I'm going to show you how to use it for rare event calculus. And my friends mathematicians told me that there is a name for that, which is Friedlin-Wenzel theory. But since I myself cannot read their books, I put a little question mark here. I really don't know. And in the end, I hope I will tell you a little bit about phase transitions and classification of the phase transitions in these systems. All right, so let me show you an example, just to introduce notations. I will focus for a while on a single side of the lattice, so there is no spatial degrees of freedom for a while. And I have a couple of simple rules. I may have branching, A goes to 2A with a certain probability mu, rate, should I rather say. And there is annihilation, 2A with certain rate lambda may go to 0. Right? Then the first thing, of course, which comes to mind is to write down a rate equation, which is change of the density in time. It has two terms, one coming from branching, another coming from annihilation. And you immediately see there is a stable point in this equation. So if you start from some initial condition and not, then you will exponentially fast go to a stable point ns. Okay, that's kind of a deterministic level of a description which completely neglect this discreteness of agents. And of course, it's not true. I mean, first of all, we understand that there is entire probability distribution at any time t. I may have in principle any number of agents, and I just have to tell you what is the probability to find given number of agents at a time t, and it's not necessarily this one. And second, you understand that if you wait for a long time, then accidentally the last, if you start, accidentally the last agent will be annihilated, and then the system cannot recover from the empty state. So at a long time, there will be an extinction, which is completely not in this, of course, rate equation description. So one of the questions is how long you should wait before extinction happens. Okay. All right. So now, how to approach this type of problems? There is an, in principle, exact way of talking about this system, which is a discrete master equation, which is an evolution equation for probability distribution function to find n agents in time t, and it has very simple structure. It has in and out terms. For example, for branching reaction, in process is that you come to the state with n particles from the state with n minus 1 particles, and that happens with a rate which is proportional to the number of particles in n minus 1 particle state. And you go out with a rate which is proportional to the number of particles in this state. And then for annihilation, it's two similar terms again, in and out. You come in from state with n plus 2, you go out from the state n, and those are the rates, which are just number of pairs. A pretty trivial thing. All right, now this is a simple example. It can be basically pushed brute force, but it's not interesting. So what is useful is to think about generating function.
That's in 0 dimension?
I'm sorry?
0 dimension?
Yeah, this is so far 0 dimension. I will come back to the latest, to a latest later. Okay, so just to introduce notations, 0 dimension is enough. Okay, think about generating function, which is a function of little p auxiliary variable, which I call little p, and excuse me for doubling of p's. This one is going to be a momentum in a short while, so I have to call it p. And this one is a probability, I also have to call it p. Very little choice, right? Okay, so this is a formal definition. So what you understand is that if you put this little p to be 1, then you have just conservation of probability, so this generating function must be always 1 if the first argument is 1. Another observation is that if you put p to be 0, then you're talking about p0, and this is exactly extinct state, where there are no particles in a system. So if you want to think about extinction, you need to know just this generating function at 0 value of an argument. All right, then you can substitute this definition into this discrete equation, crank some trivial algebra, and instead of discrete finite difference equation, you're going to have continuous differential operator, in this case of the second order. You can easily understand that these combinations like n plus 2 times n plus 1 are generated by application of a second derivative to the generating function. Okay, so that's some progress. Instead of this finite difference, we have continuous differential operators, still not very appealing. Here it is again. Now, you can have a progress if you realize that it is an imaginary time Schrödinger operator. Okay, just analogy. So t is now imaginary time from the point of view of a Schrödinger. This differential operator I will call Hamiltonian, and it is a function of little p and operator q, which is nothing but ddp, differential operator with respect to p, and there is a canonical commutation relation, of course, between them. So my Hamiltonian is normally ordered, p always to the left of q, which is a good news. It is non-Hermitian, which seemed to be as a bad news, but actually it's not such a bad news. All right, now what to do with that? So the way I like to think about it is to put it in a kind of Feynman path integral representation.
To say it's non-Hermitian, you must have made some choice of scalar product. Which one did you choose?
Scalar product.
Well,
I mean,
without scalar product, there's no Hermitian adjoint. Can't say what.
Right. Look, it's derivatives acting to the right. So I can have a right eigen functions. Okay.
So you're thinking of it as an L2 space in
Yes.
P variable. Okay. Well, there could be other choices. Maybe there's one that makes it Hermitian.
Maybe. I don't know what is it good for, but maybe. All right, you will tell me. All right, so if you think about a solution of this Schrödinger operator in the form of a Feynman path integral, you may think that among all possible trajectories in PQ, P of t and Q of t, the most prominent one is a saddle point trajectory. So namely, you think about, oh yeah, before that, so let me mention that for any reaction NA to going to MA, you can always do the same, you know, procedure. You can define a Hamiltonian which has this simple form. And there are a couple of generic things about this Hamiltonian. If you put P equal to 1, you must get 0, and this is because if P equal to 1, you have normalization of probability. It shouldn't evolve. The generating function is always 1 if P is equal to 1, and so that means that Hamiltonian must be 0. There is no evolution at this point. And then there is another almost generic property is that if you don't have creation of particles from the vacuum, if you put Q to be 0, it's again 0. Right? So if no particles are created from vacuum, if this n is never 0, then it's always proportional at least to the first power of Q. All right, now back to solutions. So what I will do, I will think about WKB solution of this Schrödinger, quote-unquote, Schrödinger operator. Or, again, this is just a saddle point of my Feynman representation. So if you put it in the equation, then, of course, as any WKB, instead of Schrödinger equation, you get a Hamilton-Jacobi equation. So ds dt is this Hamiltonian, P and ds dp instead of a coordinate. So instead of now standard procedure, instead of solving Hamilton-Jacobi equation, it's easier to think about just Hamilton equations, find trajectories of the Hamilton equations, classical, and then find the action, and then put action in the exponent, and you will know that your generating function.
What is the semi-classical limit here?
Sorry?
What is the semi-classical limit here?
You mean what is a parameter which you control? It's sort of a volume of the system, right? So this average number of particles, ns, must be bigger than 1. Okay, so inverse Planck constant is this ns. Now there is you have to specify boundary conditions for these classical Hamiltonian equations, and it depends on what problem exactly what question exactly you ask yourself, but typical, you fix a coordinate in an initial moment of time, and then you have to fix this momentum at the finite moment of time, okay, where you calculate your observable. That requires some careful discretization and consideration, but believe me, that's a typical way of choosing the boundary conditions. All right, so for example, which I gave you below, above, so this is this Hamiltonian, which, by the way, doesn't have a standard form p squared plus v of q, which we all know and love. It's some complicated, well, not really complicated, polynomial of p and q. You write down the classical Hamilton equation. They're still not very appealing. I mean, you can solve them, but it's not immediate to understand how it behaves. Fortunately, we don't have to do even that, because there is a constant of motion, which is an energy, right? And we can classify all the solution according to this integral of motion. And all what we have to do is just to plot a phase portrait, lines of constant energy in a coordinate space P and Q. Okay. Yeah, one thing which I forgot again to mention is that if you put P equal to 1, this special point where you keep normalization, keep conservation of probability, then your classical, the second equation for P becomes trivially satisfied, but the first equation give you your old friend rate equation. Okay. So the rate equation, which we started from, which was deterministic description of the system, is nothing but a particular case, particular solution of this system of two equations. Okay. So now, which one where you restrict P to be exactly 1? Now, if you don't restrict P to be exactly 1, then you have entire phase space. And for this particular Hamiltonian, you have that kind of topology. Yes.
There is something in my mind. If I don't understand it, then I cannot listen. You start with you had a statement that the quantum mechanics that you have is not self-adjoint, so it is doesn't conserve probability or is not unitary.
No, that I didn't tell you.
It is not. If it is not self-adjoint, how can it conserve unitary? How can it be unitary? And then the question is, you have Hamiltonian, which conserves phase space volume, so it is conserved.
Yeah.
So if you took this one and you quantize this one, would you get, like if you quantize properly this one, you'll get self-adjoint operator, I believe. So is the loop not closed? So if you translate from Hebrew to Chinese and then again from Chinese to Hebrew, then you don't get Hebrew. I'm afraid I don't understand how you.
So first of all, about probability conservation.
Sorry?
So your probability is not psi square, right? So it's not the usual scalar product of psi. Okay.
So that comes back to the question of Martin. What is the scalar product?
Yeah, I mean, in some sense, you don't need this scalar product because you're not going to form psi times psi. All what you need is a green function. Okay, and conservation of probability is sitting in the fact that when you put p equal to 1, this guy is 0. Okay. So my generating function at p equal 1 does not evolve at all. I mean, you started from being 1, it will be 1 forever. And that's conservation of probability, and that's all what you need. Okay. Now, if you will try to define Schrödinger, true Schrödinger probability like psi square, then you will run into problems. You're right, but you don't have to do it.
But if I don't do that, you have this area preserved. You
Yes.
have for some brackets.
Yes.
You replace them by commutators. What
Yes.
happens then?
I mean, you instead of having classical equation, you start having functional integral.
Yeah, you
And
have
all
to-
what you need to exponentiate it is a normal ordering.
It's not unitary group, it's just Markov semi-group. That's it. No quantum mechanics. It is a Markov semi-group. And the operator is an infinitesimal generator, that's it.
Is there any need to respect the mechanics?
No direct.
Look, you don't want to call it quantum mechanics, don't do it. I mean, it's simply solution of a first order evolution operator. Okay, so.
That's the trick to do this classical mechanics.
Yeah, but if it's distracting trick, let's don't think about it. For me, it's useful.
Well,
All right.
I should make a cultural remark. In this statistical physics field, most people don't think about quantum mechanics, and that's why they always use the same method for Kaplan equation or eigenfunction mechanics. So what's useful in this business is, and many ideas and concepts which we are familiar with, quantum mechanics, we can sort of transfer to this field, and that's just a sociological statement. People just don't do it because they don't draw this connection. So one runs into this problem, hermeticity and so on. But it's good to know that there's a toolbox of quantum mechanics. That's what it's about.
All right. So forget for a moment about quantum mechanics. Let me try to give you some intuition about classical mechanics of this Hamiltonian. Okay, and it's a little bit unusual compared to p squared plus v of q, which we all know from high school. So there are a few lines of zero energy. One of them is completely fundamental. It is this p equal 1 line, and Hamiltonian must be 0. So this evolution can, of course, preserve this line. It's a constant of motion. And it has stable point. That was our stable point, mu over lambda, which I showed in the beginning. And then there is a formally unstable point at 0 number of particles. According to this classical mechanics. Of course, quantum mechanically, we understand that there is extinction, and once you come here, you will never leave this point. Right, so by the way, from this analogy with rate equation, you can think about Q, which was introduced completely formally like DDP, as a coordinate, as a number of particles. Okay? At least at this line, P equal 1, it's really an average number of particles. All right, now there is another line of zero energy at Q equals 0, which come from the fact that no particles came created from vacuum. And then there is a third line, which in some sense accidental, which connect this stable point here and some point at Q equals 0 axis. Okay, so now how would you ask about a rare event in your reaction diffusion system? You fix initial, yeah, here it is again. So you fix your initial number of particles, let's say this one. And you say, I want to find probability of extinction in a given time. Okay, so you will need to find a trajectory which connect your initial Q with your final P. At finite time, you fix P. Okay. If you talk about extinction, then P is equal to 0. So some point here connect to some point there, and you need to find a proper trajectory which does it in a given time. Okay. For example, if you don't care what time it is, if you can give the system all time in the universe, it will do it along the trajectory of a zero energy. Okay. And if you're interested in extinction time, you need to calculate an action, which is nothing but the area of this triangle, so to say, and extinction time will be exponential of this area, okay? Which happen to be this parameter ns, average number of particles, times some idiotic number, whatever it is. So now you see that for validity of this semi-classical approximation to be there, this ns has to be big, and this is my inverse Planck constant.
Why is this grid area extinction?
This is an action, right? And our generating function is e to the minus action.
Normally it's integral dv Q, and here it's integral qdp.
Yes.
Same thing.
Okay, this doesn't matter, but because area preserved, so
What?
this map, right? This area between
Evolution is area preserving, but what you're looking for a particular trajectory which answer the question which you ask. So in particular, if you ask a question about extinction, you need to find a trajectory which connect your initial point to finite point, and then you calculate an action, right? So if you are doing mean field, then you're always moving along this line, the action is 0, so those events are not exponentially improbable. Those have probability of order 1. All right. So then you can, once you understand this, you can start playing with it. For example, you can solve time-dependent problem. You can ask, what if one of my rates, or both of them, doesn't matter, are explicit function of time, right? So, for example, your reproduction rate is decreased for a while. Okay? Then you understand that during this period there is an enhanced probability to go extinct because reproduction is less effective. And you ask yourself how much probability to go extinct is during this period. So okay, you have this Hamiltonian phase portrait before catastrophic event come. Then once the catastrophic event came, you have a new Hamiltonian which has basically the same topology but somewhat smaller. The stable number of particles in this time frame is less than its initial value. So from time A to time B, you propagate along one of the trajectories of a new Hamiltonian instead of propagating along the trajectories of an old Hamiltonian. So all in all, your extinction trajectory now follows the extinction line of an old Hamiltonian, then for a while follows one of the trajectories of a new Hamiltonian, and then complete the extinction along the trajectory of again of an old Hamiltonian. And The only thing you have to do is to find the proper trajectory which from A to B takes exactly the time between A and B. Okay? So again, I mean, never mind details, but virtually any equation you can ask boils down to some classical mechanical problem, maybe time-dependent classical mechanical problem of this strange Hamiltonian. And again, all what you have to do is to calculate the action along this trajectory, basically the area, and that will be the answer on your question, what is the extinction probability during this catastrophic event. All right? Okay, that's numerical simulation for more realistic shapes. All right, so here is an example of a system with more than one type of particles. So here is two types of particles. I have susceptible individuals and infected. So the and again, rules of the game is that susceptible can die, they can be born. If susceptible meets infected, there are two infected, and then infected can disappear. So if you simply write down coupled rate equations for this system, you will find that its dynamics is given by this nice spiral. There is this unstable fixed point where you have certain number of susceptibles and no infected in your population. Now, if you introduce at least one infected individual, there is an outbreak of an epidemic. Number of infected goes up, then epidemics winds down, and then there is a second outbreak of an epidemic, a third outbreak, and in the end of the day, it collapses, spirals down to the stable fixed point in the rate equation level, stable fixed point, where you have a certain number of infected individuals in the population and significantly smaller number of susceptible because part of them was lost during this epidemics. Okay. Now this is rate equation again description. Now if you go to the full stochastic problem, you understand that this point is not fully stable, and there is a probability that your disease, your epidemics, will go extinct. Namely, you will go against the flow, and you will come down to this point again. Okay. For that, you have to double number of degrees of freedom. In addition to this S and I, you have to introduce two momenta and solve a problem in a four-dimensional phase space. Okay. Namely, you have to find a classical trajectory of zero energy, which starts from this point and ends up in this point, but this is a trajectory in four-dimensional space. Okay? So this trajectory was purely in two-dimensional. This is a mean field. This is an analog of this vertical line which I had on a previous slide. Okay. Now, if you look how it looks like, so its projection of this four-dimensional trajectory again in a plane of I and S looks like this. So this is how epidemics go extinct, how you go from this point back to that point. Notice that you go it again in an oscillatory way. And so it's now spirals out and then ends up here. But again, this is a four-dimensional trajectory, so this is another projection of this four-dimensional trajectory on a plane of two momenta, Pi and Ps. And again, it's a relatively simple thing. You can find this trajectory, and you can calculate an action, and the exponent of this action will tell you what is the time for epidemics to go extinct. All right? Okay, so that's kind of a game which you can play. Now, that's time to go back to the lattice. So now, if things are on the lattice, then both Q and P has additional index, which is a lattice site. I call it X, but it's in principle discrete. And then your Hamiltonian is now sum over all lattice sites, reaction Hamiltonian. Reaction is supposed to has the same rules at every site. And then there is a diffusion. Believe me, it's a simple thing to show that diffusion is translated to product of two lattice gradients of P and Q. Okay. So now instead of quantum mechanics, you have sort of quantum field theory. Okay. In addition to time, you also have space. Now you can look for classical solutions of this quantum quote-unquote field theory, and you will get equations of motions for coupled Q and P. Q has a form of nonlinear diffusion equation. P has a shape of nonlinear diffusion equation with negative diffusion constant, which seem to be an alarming feature. But remember that P is fixed in a finite moment of time. So P always propagates back in time, and Q propagates forward in time. So this negative diffusion coefficient is actually a good thing, not a bad thing. Again, if you put P equal to be exactly 1, then the second equation is satisfied identically. And the first equation is what is frequently called reaction-diffusion equations, and many people spend lives solving them. What I'm trying to tell you here, but actually it's not one equation, it's two equations. And if you ask for not a typical event, for rare event, you have to solve both of them, not just this one. Okay, and then I'll probably skip these examples. You can find space-dependent solutions of these classical equations. Well, that they will be, so to say, instantons of this quantum field theory, but I don't have much time, so let me better skip it and go to phase transitions. Okay, so now the nice thing about these systems is that if you put it on a lattice, and this lattice is really big, you may have phase transition. Namely, at any finite lattice, as I told you, this type of the game will go extinct. It's just a matter of time. You wait for a long time and everybody will die. But if you first go to thermodynamic limit, then it's not obvious anymore. In particular, one side may go extinct, but then particles from neighboring sites will diffuse there and will repair sort of stable population. So in the end of the day, it boils down to the comparison of diffusion rate and extinction rate, and either of them can be bigger. So you may have either global extinction or global quasi-stable phase. Okay, when you change some parameters. So here is a simulation in one spatial dimension and time. If reproduction rate is small, this mu is small enough, then after some time everybody goes extinct. If reproduction rate is bigger than a certain critical value, then you have a certain stable population, and there is a critical value where you have sort of in between. Now, if you look more closely and you, for example, plot what is this quasi-stable population as function of deviation of mu or any other parameter from a critical value, you will find very nice power laws. This is a logarithmic scale, so they are almost flat. So there is a critical exponent beta, which tells you what is a stable population as a function of deviation from a critical point. You may also define correlation lengths in time direction and in space direction, and they both diverge, again, as a certain powers of deviation of a critical parameter. Numerically at least, there is a complete analogy with second order phase transitions, right? So there is a zoo of critical exponents. They strongly depend on dimensionality. So this is beta is an order parameter exponent. Nu parallel is a correlation length exponent in time direction. So for this particular model, which I'm telling you, they are known from tremendous accuracy. And for d larger than 4, they both 1, and this is kind of mean field value, which you would naively predict.
How
Just
did 4 come here? How did 4 come in this model?
as a critical dimension.
Yes.
You'll see. Oh, whatever. I'll tell a bit later.
Well, paths don't cross, right? Paths are unlikely to cross.
No, that will give you 2, I believe.
What do you mean? No. Why 4?
It's a
There's a
critical.
probability of 2 paths crossing. The Brownian motions don't cross in 4 dimensions. They do in 3.
Why not 3?
No, that may be a reason, but I never thought of it as being the reason. you'll see. I mean, if you do a simple scaling,
Okay.
it's obvious.
Comes out
But
from scaling.
all right. Yeah. If dimensionality is below 4, then exponents strongly deviate from the mean field value, and here are they. Now, so the question which I want to address in the last, whatever, 10, 15 minutes I have is what is a way to calculate this critical exponent analytically, if any. Now, it looks like a certain universality class in terminology of second order phase transition. So what it is and what other reactions can belong to this universality class and what are other possible universality classes, and all these usual suspect questions about second order phase transition. All right, now we perfectly know how to approach it in equilibrium models, where we have a field theory which is formulated in terms of a single order parameter. Let me call it Lagrangian field theory. We have this diffusion term, and we have a potential. Okay. Now, what Landau tells us is that let's forget about spatial dependence on this phi and simply plot potential as function of spatially uniform phi. And this potential may have either one minima, and then this is a kind of disordered phase, or it may have or it may have two minima, and then this is an ordered phase, and all that we have to do is to invent the simplest cartoon which interpolates between two minima and one minima. So it's phi to the 4 potential, and this parameter m is a critical parameter, depending whether it's smaller than 0 and larger than 0. We have one or another scenario. And then what we're supposed to do is to allow for spatial fluctuation of this phi, integrate them out of the problem scale by scale to do the normalization group, maybe epsilon expansion, and what we will find, of course, that the critical dimension is 4, and if 4 minus d is small, then we can systematically calculate critical exponents. Now, the question is what come instead of this paradigm in this reaction diffusion system. So you can frequently see this trick of going from d spatial dimensions to d plus 1 spatial dimensions, including time, Euclidean time, but otherwise leaving the theory pretty much unchanged. And what I'm arguing is that's probably not a very good idea in general, at least. So, because what we better think about is a Hamiltonian field theory, which has 2 degrees of freedom instead of phi. We have P and Q, and there is this reaction Hamiltonian. Now, again, following the same route, we're supposed to say that P and Q are uniform, spatially independent. Let's plot this H. Now, that's not simple. I mean, how would you plot a function of 2 variables? But fortunately, again, you don't have to do even that, because recall my phase portrait. So what was important in all this zoo is the web of lines of zero energy. So what is important to characterize this field theory is simply to understand that the Hamiltonian has a following 3 lines which has zero energy, and they intersect like a triangle. Okay. Now, going to the phase transition, towards the phase transition, is changing some of the parameters in this Hamiltonian, which will change the topology of this triangle to something like that, then to something like that. This is a critical point, and then to something like that. This is a disordered phase, so to say. Okay? So this picture comes in instead of going from this to this to that in a Lagrangian field theory. Okay, so now in a Lagrangian field theory, we knew how to proceed. Let's invent the simplest cartoon which will do that interpolation between 2 minima and 1 minima, and parameter will be a critical parameter. So you can employ the same logic here. So let's do the simplest cartoon which has these 3 lines of zero energy. So it will have P for this line, it will have Q for that line, and it has some linear structure for the third line. And the critical parameter is this free coefficient m. So once you change it, you move this line from below to above. And m equal to 0 is the critical point. Okay? So what I'm claiming that this cartoon is a proper way of thinking about non-equilibrium phase transition. Okay? Yeah, that's a critical parameter. Now it's actually known. I mean, I'm not inventing here a bicycle. So the fact that this very field theory is the prototypical model to describe this phase transition, which is, by the way, called directed percolation, is known for already more than 20 years. First realized by Jensen and then Grasberger and Carty. And I will probably skip explanation why it is directed percolation. Now, then you can do, once you realize that all what you have is this triangle and you have to renormalize it, you can do a standard renormalization group. You simply think how upon integrating out fast degrees of freedom, this phase portrait changes. Okay? Evolution of this topology upon integration of smaller and smaller scales. And in particular, one loop renormalization group is given by this simple diagram, which you can form from these vertices of the third order. And by the way, all the set of these Feynman diagrams will generate what is called directed percolation, and this is by the name. So the naive scaling will immediately tell you that critical dimension is 4. First order epsilon expansion will tell you that beta is 1 minus epsilon over 6. Numerical data is 0.81, which is pretty close to what you find here. But again, in that sense, this is not better or worse than the standard epsilon expansion. Okay, now what is it good for? Now you can start thinking what can be other universality classes. For that you need to think what other topology of the phase space you can imagine. Right? For example, you could think that instead of triangle you may have kind of rectangle or something, and then you change some parameter and then this rectangle will collapse to a point. Okay? But then thinking a little bit, you will realize that this is not a generic situation. By changing one single parameter, it is unlikely that you can put 4 lines to intersect in one single point. Okay? You need at least 2 control parameters to achieve it. Okay? Unless you have an additional symmetry in a problem. Okay? And there is a number, but very small actually, number of possible symmetries which allow you to do it. So one of them is that you start all the reactions from at least k particles. And that what this will do, it will make this horizontal line q equals 0 k times degenerate. So instead of p times linear function times q, you will have this q to the power k. Okay? And then you change your critical parameter, you collapse this structure. So in a sense, you push 4 lines to intersect in one point. Okay? And that's known, again, numerically known to give you a different universality classes. And then, this is a rather famous example among numerical people. So there is the same binary annihilation, but the second reaction is 2a going to 3a and back. So all reaction starts at least from 2 particles. That give you a phase portrait of that topology. Critical dimension will be 4 over k, so in this case it will be 2, and critical exponents are different. All right, there are a couple of other ways. For example, if you consider all reaction to be parity conserving, all reaction change the number of agents by even number, 2a to 0 and a to 3a. Okay, you conserve a parity. So what it translates to, there is a symmetry point in the beginning of a coordinate, and your phase portrait must be symmetric with respect to reflection, with respect to the origin. Okay, so that excludes the possibility of moving this line and sort of crossing this point. Okay, all what you can do is somehow just deform this line. Okay, and you can realize that since there is this constraint, probably universality class should be different, and indeed you can do a cartoon field theory for this run renormalization group and see that it has different epsilon expansion, and this was done actually by Cardi et al. There is yet another universality class which was not appreciated before our work. If all reaction is sort of reversible, for example, 2A go to A and A goes to 2A, then the topology is this rectangle which cannot be broken, and phase transition correspond to collapse of this rectangle. So in this case, it's a stable thing. All right. You can also discuss first order phase transitions in the same language. First order phase transition would be evolution of the phase portrait like this. You have this mean field line which predict that the only stable state is 0, and then you change some parameter and some other line cross your line at a finite point A. So now you start having a stable population A. Right, so that's an example of a first order phase transition which you can think. So anyway, all this Landau type of logic with potential which has one minima, two minima, they collapse or they intersect places, can be basically translated to this two-dimensional Q and P times Hamiltonian field theory instead of Lagrangian, and I think it's much more useful than D plus one-dimensional Lagrangian field theory. All right, so finally, what I hope to show you is that there is a Hamiltonian language to describe these games or reaction diffusion models, and I try to tell you how to use it to develop calculus of rare events and how to think about phase transitions and their classification, basically, thinking about topology of a phase space of a Hamiltonian. Thank you.
So the Hamiltonian is non-Hermitian. Is it pseudo-Hermitian?
Which is?
So it's a mathematical class. You multiply on both sides by a constant operator, and you come up with the relation to the original.
I don't know.
Any other questions?
One describe driven systems where you inject particles somewhere, take out particles somewhere.
Yes. You can do it.
Then the instanton is not anymore the reverse of that.
Yeah, in any case, instantons here are not time-reversed partners of relaxation, like an equilibrium. In that sense, there is nothing new in there.
So you can drive the system and
Yes.
take stuff out, and then in this case, are there phases where you can just describe the invariant measure? I mean, do you always work in the time-dependent formalism, or is there a steady state that you can describe?
You can describe steady state, of course.
Is it Gibbsian or?
So if you ask what is a probability of a given configuration which
Yeah, in
deviates
steady
from,
state, yeah.
no, it's not.
But you can describe this. You can.
If you give me a given spatial configuration and ask what is its probability,
You can.
in general there is no way to express everything just in terms of space. You have to find
So you
a
really
dynamical
have to
evaluation.
work in
Yes.
the space-time picture.
Yes, you have to work.
That was
yes,
really my
yes.
just
In
my
general,
question.
that's the case.
Everything has to
Yes,
be formulated
yes,
that way.
yes. Unless there is exact integrability or something, then you can.
Any other comments or questions? Well, maybe somebody could could say, make a comment about the connection with Wenzel-Friedland theory, Alain?
Author can.
Oh,
Sure. On the lattice, I have no idea. Of course. Original system, yes. The lattice, the one that we had with the
You
action.
mean with the
It's finite dimensional.